Welcome to this video, which is focused on exercise 6 of chapter 12. This exercise is all about the grid search algorithm for fitting models to data. Now, there's a lot of text here, so there's a lot of instructions here, but I'm actually going to explain the goal of this exercise by showing you figure 8. So let's look at that figure here. Let me zoom out a little bit. So we are going to be using the happy student data set. You'll remember this from the previous chapter. This was this fake data set with fake numbers, fake conclusions, where we were trying to predict life happiness as a function of the number of my online courses people have taken. Totally fake. I made it all up. Okay. Now, in that case, we're using regression. We set it up as a regression problem, and we use the least squares method to solve that problem, to find the optimal parameters of that model to best fit the data. Now, when you have a linear model, then least squares is the best way to go. It gives you the best solution. Maybe you need some regularization or something, but least squares is the right solution. But if you have a nonlinear model, then you cannot use the least squares approach. Why not? Because least squares is based on linear algebra, which is limited to linear problems, linear equations. So if you have nonlinearities in the model, you will need to use some alternative methods to fit the model to the data to determine the optimal parameters. And there's various techniques you can use. You can use some kind of a nonlinear transformation. You can use grid search, which is the method we are going to focus on here. I'm sure you've also heard of gradient descent. This is the most popular method for finding optimal parameters in artificial neural networks and deep learning and so on. Okay, so here we are going to explore grid search. Now, in the text surrounding this figure, I explained how to implement a grid search method. And the concept is really simple. I'm just going to explain it again now. You can see this is, we have a grid here. We have lots of different values of slope, lots of different values of intercept. And that means that there are, I don't know, some hundreds or tens of thousands maybe of pairs of slopes and intercepts here. And so we build the model using, let's say this particular slope. So a slope of 2 and an intercept of 20. And then we predict data based on those two parameters and then compute the fit of the model to the data. And in this case, we're using the sum of squared errors. In the next exercise, so the next video, we will explore using R squared. But here we are just using the sum of squared errors. Okay, so it turns out that the fit of this model with these two parameters to the empirical data is quite high. So this is actually not a good set of parameters. So then what do? Well, we go to the very next pixel here. So a slope of 2.1 and an intercept of 20. And you see where this is going. We just repeat this in a double for loop over all of these different pairs of parameters. And then basically you look through this entire space and you find where is the minimum. The minimum sum of squared errors corresponds to where the model with these parameters fit the data the best. So that is how grid search works. Very simple, very straightforward, very intuitive and easy to understand. It's not necessarily a scalable method because it's very computationally intensive. But it works really well when you don't have so many parameters to fit. Okay, so that's the goal of this exercise, and now I'm going to switch to Python and show you my solution. Here we have the data again, so the number of courses and life happiness, and these numbers are literally copied from the previous chapter, so nothing new here. Okay, and here I create the design matrix. Now, these beta coefficients, this actually comes from a least squares fit. So this is the analytic solution. This is the solution that mathematically we know is going to be the best solution. And it's useful to compute this because that is going to be compared to the solution we get from grid search. Okay, so here I have a grid resolution of 100. And so this means that when we have two parameters, there's 100 different intercepts between 0 and 80, and 100 different slopes between 0 and 6. And so now all possible combinations is 100 by 100, which gives us 10,000, right? So it's 100 by 100, which gives us 10,000 different parameters to test. And that's only for a model with 2 parameters. And we already have 10,000 models to test. So this gets really computationally intensive. Okay, here I have the sum of squared errors as a matrix for all the intercepts and all the slopes. And let's see, yeah, here I compute the model predicted data. So it's the design matrix times this vector, where this vector is defined by this particular intercept and this particular slope, and then compute the sum of squared errors here. Now, what you can see is that there is no inversion. We're not inverting the design matrix. We're not computing least squares. We're not calling any functions that will compute least squares for us. There's no least squares in here. There's no inverse. There's no left inverse. Instead, we are simply jumping right to the predicted data step and then compute the error between the predicted data and the observed data. So that's the idea. You don't need to implement any model fitting here. Okay, this is just a little bit of code to find the empirical minimum of this function. Okay, and then I'm just showing that function. So that you see here, this just reproduces the figure that I showed in the book chapter. Now you can see that the two solutions here are close. They're not exactly the same. And they're not exactly the same. You have that printed out here. They're very close. They're not exactly the same because of the resolution. So to illustrate that to you, I'm going to reduce the resolution to 20. So now this model is going to run much, much faster because instead of 10,000 steps and models to evaluate, there's only 400. And now you can see that the match is still sort of reasonably okay, but it's further apart, which means that this grid search solution is actually worse than it was before. And those numbers aren't there anymore, but you can see that was 3.76 compared to 3.70 from the analytic or the optimal result. So this highlights one of the difficulties of this empirical method. And let me set this up to, let's try 200, increase the resolution a bit. So there's a trade-off here. If you have a higher grid resolution, you'll get more accurate results and also a nicer looking plot. But it takes longer. Again, in this case, it's a simple model with 2 parameters. It's not so computationally intensive. But imagine if you had a 10 parameter model, this would take a really, really long time. So then that would make you want to reduce the resolution. But if you reduce the resolution, you might not get the right results or the optimal result. Another limitation of the grid search method is you have to already start with a pretty good idea of the appropriate ranges of the parameters. So for example, imagine that we had, actually, you don't even have to imagine, we can just change this. So I'm going to say the slopes is, I'm going to allow the slopes to vary between, let's say, -2 and +2. That's, if you don't know anything about the nature of the data, you don't know anything about the problem, you can do this. And then, now the result is really bad. I mean, this is just a terrible result. And the issue here is that we are searching in the wrong place. So that's another limitation of this grid search method. Again, there are ways around this. So, you do an initial coarse grid search to get an idea of an appropriate range, and then you would zoom into that range and you would do a more finer, granular approach to get a more accurate answer. So, the field of grid search methods in applied mathematics and optimization in machine learning is big. This is just a general introduction. But still, these problems are important issues to think about.